today's video we'll discuss about alcohol, phenols and ethers. Alcohol are represented by the general formula ROH, where R is an alkyl group. And further, we can classify these alcohols into different types. So if you consider a simple example, CH3OH, then similarly CH2, CH2, OH and OH. So one OH means monohydric, two OH is dihydric. Next is CH2, CH, CH2, OH, OH and OH. Since three OH groups are present, it's a trihydric alcohol. And phenols, so for an benzene ring, if OH group is directly bonded, we call it as phenol. Similar to alcohol, even phenols are monohydric, dihydric if two OH groups are present, and trihydric if there are three OH groups present onto it. So based on the number of OH group, we classify them as monohydric, dihydric and trihydric. Next we'll consider ethers. So ethers are represented by the general formula ROR, where R can be either a alkyl group or it can be even an aryl group. They are further classified into two different types. So what are those we'll discuss, but before that, alcohols. So alcohols are further classified based on the nature of the carbon OH bond, that is carbon containing sp3 hybridized OH bond and sp2 hybridized OH bond. Alcohols are further classified as primary, secondary and tertiary alcohol similar to alkyl halide, as well as compounds containing sp3 hybridized carbon OH bond. Two more types we know, that is allylic alcohol and benzylic alcohol similar to that of alkyl halides, which contain sp3 hybridized carbon OH bond. And sp2 hybridized carbon OH bond is present in vinylic alcohol as well as in phenols. So similar to alcohols and phenols, ethers based on the nature of the R group, they are classified into simple ethers if R group are same, if both the R group are same, and mixed ether if there are two different alkyl or an alkyl and aryl group bonded to it. So two R groups should be different. Simple ethers are also called as symmetrical ethers, whereas mixed ethers are also called as unsymmetrical ethers. So this was regarding the brief classification of ether. Next we'll go with preparation of alcohol. In that, acid catalyzed hydrogenation. So the reaction occurs in the presence of acid and the addition of H2O takes place according to Markovnikov's rule, which states that the negative part of the attacking reagent should get bonded to the carbon atom containing least number of hydrogen in carbon-carbon double bond. So the negative part OH minus attaches to CH carbon as it has least hydrogen, and the product is CH3CHOH, double bond becomes single bond and CH3, and hence we obtain alcohol as a product. So in the presence of acid, addition of water occurs. Then the next reaction is by hydroboration reduction, which takes place against Markovnikov's rule, hence we call it as anti-Markovnikov's addition. So anti-Markovnikov's rule, here it is opposite to that of Markovnikov rule. Here we see that boron gets attached to a carbon atom having higher hydrogen atom, and here we see that three different alkenes are reacting. So we'll write the reaction here. So this is our first step. One product we have got, that is monoalkyl borane. It is made to react with another alkene, propene. It results in the formation of dialkyl borane. We'll write its formula. So CH3, CH2, CH2, and one of the hydrogen of it is substituted, so it becomes twice BH. When this is made to react further with another alkene, that is propene, it results in the formation of trialkyl borane, which we will represent it as CH3, CH2, CH2 thrice and B. And when this trialkyl borane is further made to undergo reaction with hydrogen peroxide in basic medium and in the presence of H2O, we see that the product obtained is an alcohol, that is alkyl alcohol, CH3, CH2, CH2OH, that is 3 moles of alcohol we get. Along with it, the byproduct obtained is BOH thrice or nothing but H3BO3, which is orthoboric acid. So primary alcohols are obtained as product by hydroboration reduction. We'll go with the next method of preparation, that is reduction of aldehydes, ketones and carboxylic acid. So whenever reduction of aldehydes occur by addition of hydrogen in the presence of catalyst, one hydrogen gets added to carbonyl carbon, another hydrogen to the oxygen, and the resulting product we get it as already we have CH, it becomes CH2, double bond becomes single bond O and H, and we see that it's nothing but it's a type of a primary alcohol. So you should remember that whenever aldehydes undergo reduction by addition of hydrogen, either addition of hydrogen in the presence of catalyst or any reducing agent, we see that they form primary alcohol. Next, we'll consider ketones. Ketones undergo reduction in the presence of reducing agents or even addition of hydrogen, and here hydride means that hydrogen is added, one hydrogen to carbon, one hydrogen to oxygen, double bond becomes single bond, and ketones result in the formation of secondary alcohol. So secondary alcohols are obtained as a product. Ketones from secondary alcohol, aldehydes from primary alcohol. Similarly, now when we consider carboxylic acid when treated with lithium aluminum hydride followed by hydrolysis results in the formation of primary alcohol. But this is not industrially used because lithium aluminum hydride is an expensive reagent. Since it is an expensive reagent, industrially the process followed is first is esterification reaction followed by addition of hydrogen. So when esterification reaction occurs, that is by making use of an monohydric alcohol, we get the product as ester. And this ester on addition of hydrogen results in the formation of primary alcohol, giving back the alcohol which was used in the esterification reaction. Hence this is an industrially used process which gives you primary alcohol from carboxylic acid, not directly but by first carrying out esterification and then hydrogenation. So this was regarding the preparation of primary alcohol from carboxylic acid. Next is from Grignard's reagent. So we see that in Grignard's reagent, alkyl group having partial negative charge gives electron pair to carbonyl carbon, double bond shifts onto oxygen, and oxygen gives it the electron pair to magnesium, and the resulting product can be represented as. So here already 2 bonds with carbon, a new bond is formed by an alkyl group, double bond becomes a single bond, oxygen having negative charge bonded to magnesium with plus charge and X, and this resulting product we call it as an adduct. So this adduct is unstable, it undergoes further hydrolysis. Now when it undergoes hydrolysis, the hydrogen atom gets bonded to oxygen, and the resulting product we can represent it as R already bonded to C, C having 2 bonds, OH, and another byproduct is Mg, OH gets bonded to Mg and X. So when it undergoes hydrolysis, it is addition of H plus and OH minus. So as we have seen, H plus bonds to oxygen atom and OH minus to Mg plus, and we get the resulting product as an alcohol. Now here, how this alcohol or what are the type of alcohols that are formed with the different reagents we'll see, and it is very important from your theory exam point of view. So the nature of different alcohols obtained here, for that we will consider first the reaction of formaldehyde with Grignard's reagent. So formaldehyde is represented as HC double bond OH. For Grignard's reagent, let us take the example of methyl magnesium halide. Now in this methyl magnesium halide, methyl which has partial negative charge will give the electron pair to the carbonyl carbon of formaldehyde, which is represented as double bond shifts onto oxygen, oxygen gets negative charge, gives the electron pair to magnesium, so the resulting product is CH3 is forming a bond with carbon. Carbon already has 2 hydrogen atoms which we can represent it as CH2. It was double bond, it becomes a single bond O. O forms a bond with Mg that is attracted towards Mg and X, and this resulting product we write it in square bracket, which we call it as an adduct. Now this adduct further undergoes hydrolysis. When it undergoes hydrolysis, the resulting product obtained is, so H forms a bond with oxygen, so CH3CH2 OH, and this type of alcohol we call it as a primary alcohol. Plus of the byproduct obtained is MgOHX, that is hydroxy magnesium halide is the byproduct obtained. So primary alcohols are formed whenever formaldehyde reacts with Grignard's reagent. We say that primary alcohols are formed. So always note it and remember that formaldehyde reacts with Grignard's reagent and it results in the formation of primary alcohol. Formaldehyde forms primary alcohol with Grignard's reagent. Next we will consider the next reaction. So this point you have to remember. So we'll go with the next reaction. With formaldehyde it was giving primary alcohol. So when aldehyde other than formaldehyde reacts with the Grignard's reagent, the product obtained can be represented as. So here we'll take an example of acetaldehyde or ethanol, and we'll take same Grignard's reagent CH3MgX. We know CH3 gives electron pair to carbonyl carbon. Double bond shifts on oxygen. Oxygen forms a bond with magnesium, which forms a adduct, which is represented as CH3 forming a bond with C. That C already has one CH3 and H. Double bond becomes single bond and O forms a bond with Mg plus and X. So this is adduct which further undergoes hydrolysis, and when it undergoes hydrolysis as seen above, H forms a bond with oxygen and Mg with OH. So the corresponding product here is CH3CH OH. Already CH3 was present plus of MgOHX, and the nature of the alcohol formed here is a secondary alcohol. Why? Because the secondary carbon atom is bonded to the OH group. So here you have to remember that formaldehyde gives primary alcohol, but aldehyde other than formaldehyde with the Grignard's reagent always forms a secondary alcohol. So note down this point that aldehydes other than formaldehyde form secondary alcohol when they react with Grignard's reagent, that is RMgX. Next we'll go with the reaction of ketones with Grignard's reagent. So when ketones react, what is the nature of alcohol forms? We'll see by taking the example of acetone or propanone. So when it is made to react with a Grignard's reagent like CH3MgX, CH3 gives electron pair to carbonyl carbon, double bond shifts onto oxygen. Oxygen forms the bond with Mg. So the resulting product what we get here, so CH3 forming a bond with C, CH3 already two CH3 are present, will represent that. Double bond becomes single bond O, MgX, where oxygen minus Mg plus, and the resulting product is an adduct. This adduct further undergoes hydrolysis, and when it undergoes hydrolysis, the resulting product obtained is CH3CH3 CCH3 OH plus of the byproduct obtained is MgOHX, and here if you see it's a tertiary alcohol that is formed. So ketones result in the formation of tertiary alcohol because OH is bonded to a tertiary carbon. So even note down this point that ketones with Grignard's reagent always form tertiary alcohol. So we'll conclude it. So when you conclude it, you should always know that formaldehyde with Grignard's reagent gives primary alcohol. Aldehyde other than formaldehyde with Grignard's reagent gives secondary alcohol, and ketones with Grignard's reagent give tertiary alcohol. So this you have to remember. Next we'll go with preparation of phenol, how phenols are prepared. So here if you see chlorobenzene reacts with sodium hydroxide. This reaction is even there in haloalkane and haloarene. So when it reacts with sodium hydroxide at a temperature of 623 Kelvin and 300 atmospheric pressure, it results in the formation of sodium phenoxide. It is also called as sodium phenate. And this sodium phenoxide on further acidification results in the formation of phenol. So Na is substituted by H and the resulting product obtained here is a phenol. So chlorobenzene with NaOH gives phenol, and this is the first method of preparation of phenol. We'll go with the second method, that is from benzene sulfonic acid. Benzene on sulfonation with oleum form benzene sulfonic acid. So oleum is nothing but fuming sulfuric acid represented by the formula H2S2O7. So when it reacts with benzene, benzene is converted to benzene sulfonic acid, and this is sulfonation reaction which you have already studied it in first PU. Now when this benzene sulfonic acid is made to react with NaOH, it forms sodium benzene sulfonate, which on further acidification results in the formation of phenol. So this is the second method for the preparation of phenol from benzene sulfonic acid. We'll go with the next method, that is third method, that is from diazonium salt. So when diazonium salts are formed, they are formed from aniline. Aniline are also called as primary aromatic amine. So the first step is the preparation of diazonium salt using a primary aromatic amine called as aniline. So when aniline is made to react with sodium nitrite and hydrogen halide at a temperature of 273 to 278 Kelvin or 0 to 5 degrees Celsius, it results in the formation of benzene diazonium salt. Since the halide used here is chloride, so it is nothing but benzene diazonium chloride salt that is formed. So it is represented as given below. So benzene diazonium salt, and here since it is chloride, we call it as benzene diazonium chloride. And this reaction of conversion of primary aromatic amine into diazonium salt, we call it as diazotization reaction. Now this diazonium salt on treating with warm water results in the formation of phenol displacing nitrogen gas. When it reacts with water, N2 gas is displaced and Cl reacts with H. So the resulting product obtained is phenol, and again it is important for your theory exams. So the product obtained is phenol plus of the byproduct obtained are N2 gas, along with it HCl is a byproduct that is obtained, and this is another method of preparation of phenol, that is from diazonium salt. Next we'll go with the last method of preparation, that is from cumin. Cumin is called as isopropyl benzene. Isopropyl benzene, the structure we can represent it as benzene bonded to a isocarbon. Isocarbon has two methyl groups onto it, and to it, if benzene is bonded, we call it as isopropyl benzene. So we'll consider the reaction of it. So when cumin is made to undergo oxidation, so cumin on oxidation forms cumin hydroperoxide, and this cumin hydroperoxide on reaction with H plus, that is acidification further, results in the formation of phenol. So, and along with it, it gives a byproduct, and that byproduct is nothing but acetone, or we also call it as propanone. So whenever you write the reaction, you have to represent both the products, that is phenol as well as acetone. Acetone has to be represented, or propanone has to be represented, and this reaction is important for 3 marks for your theory. Next we will go with preparation of ethers. So preparation of ethers by dehydration of alcohol. Dehydration of alcohol occurs at two different temperatures. One is 443 Kelvin, another 413. At 413 it forms ether. At 443 Kelvin, the dehydration of alcohol results in the formation of alkene plus of water. Whereas when it forms ethers, two molecules of alcohol undergo dehydration. In case of alkene, only one molecule of alcohol is involved, but when it forms ether, two molecules of alcohol undergo dehydration at 413 Kelvin, and on dehydration it results in the formation of ether represented as CH3CH2O, CH2CH3, which we call it as diethyl ether. And this diethyl ether is obtained as a product at 413 Kelvin. So remember this reaction. Similarly, at 413 Kelvin, we see that two molecules. Next, the most important question for 2 marks, that is Williamson's ether synthesis. Usually a repeated question in exam for 2 marks. An alkyl halide reacts with sodium alkoxide and forms the corresponding ethers, and this itself we call it as Williamson's ether synthesis. So this is known as Williamson's ether synthesis. Now, in this reaction, that is Williamson's ether synthesis, we see that alkyl halide reacts with sodium alkoxide. So X is removed from here and sodium from here. So the resulting product is ROR dash plus of NaX. So ROR dash we call it as ether. And here when you consider an example, similarly from here we remove Br, from here we remove Na, hence the product is CH3, CH2. From here we have removed Br, so it forms a bond with what? Oxygen, and oxygen bonded to CH3 plus of the byproduct is NaBr. So ethers are obtained as a product. Similarly, if you take sodium tertiary butoxide, it will also result in the formation of a ether, that is CH3, CH3, Na and Br are eliminated. So CH3, CH3, O, Na is removed and substituted by another CH3 plus of NaBr, and hence the corresponding product obtained is ether. But if you take a tertiary alkyl halide, it prefers to undergo elimination reaction forming alkene. So we see that alkene is formed and elimination reaction is preferred over nucleophilic substitution reaction. So instead of nucleophilic substitution reaction, elimination reaction occur, and this elimination reaction we can represent here as beta elimination. So CH3 from alpha Br is lost, and from one of the beta carbon atom hydrogen is lost. So Br forms a bond with Na, NaBr, and plus the byproduct obtained is CH3OH. So these two reactions you should remember. They may ask you to fill the products as a fill in the blank in these two reactions. So these two are important. Next we will go with another reaction, that is when phenol react with sodium hydroxide. As already seen, it forms sodium phenoxide, and when sodium phenoxide made to react with alkyl halide, it results in the formation of aryl ethers, that is OR, with the removal of Na. So the product obtained is an aryl ether. Next we'll consider the chemical properties of alcohol and phenol. Not all the reactions of it, but we'll just discuss the most important reactions. First is acidic nature of alcohol and phenol. Its reaction with metals we'll consider. So it is similar to the reaction of any acid with metal, which liberates hydrogen gas. So when alcohol reacts with sodium, it forms a salt and liberates hydrogen gas. Similarly, whenever a phenol also reacts with sodium metal, it results in the formation of a salt and liberates hydrogen gas. These two indicate acidic nature of both alcohol and phenol, as well as it is seen that when this phenol is made to react with sodium hydroxide, it results in the formation of a salt, along with that water. So it's similar to the base reaction of acid with the base, which forms salt and water. So all these three reactions indicate acidic nature of alcohols and phenol. Now among these, which is more acidic and basic, for that we'll consider the ionization reaction. Alcohol on ionization forms alkoxide ion with H plus ion, whereas phenol on ionization forms phenoxide ion along with it an H plus ion. So among this alkoxide ion and phenoxide ion, which is most stable, we'll try to find out, and based on that we'll discuss the acidic nature. For an alkoxide ion, first we'll consider that it is having my electron pair on oxygen atom, but you cannot write the resonance structures for it. And since you cannot write the resonance structures for it, this alkoxide ion is less stable. Whereas you can write the resonating structures for phenoxide ion, hence it is more stable. And less the stability, less is the acidity. So alcohols are less acidic, whereas comparatively phenols are more acidic. Thus we can draw a conclusion that alcohols are less acidic than phenols, and phenols are more acidic than alcohols. So alcohols are less acidic than phenols, and phenols are more acidic than alcohols. And why it is so? Due to the resonating structures of phenoxide ion which stabilize them. So this reason you should know. This is important for your theory exam as a 2-mark question as well as for your multiple choice question. So due to the resonance stabilization of phenoxide ion, phenols are more acidic than alcohols. Next we'll go with esterification reaction. So either a alcohol or a phenol, when it reacts with an carboxylic acid, it represents in the formation of esters as represented by the formula RC double bond OR. So alcohols or phenols, whenever they react or undergo esterification, they result in the formation of esters, and remember that esters have a fruity smell. So we'll consider the reactions here. So reaction with the carboxylic acid, alcohol, when it reacts with carboxylic acid, it results in the formation of ester. So CH3, C double bond O, O, C, H3. So this is ester, plus of byproduct obtained is H2O. Similarly, if you see even a phenol, so phenol also H is removed and substituted by an acetyl group, that is O as it is, H is removed, acetyl group is C double bond O, CH3. So here also we get an ester, plus of byproduct obtained is H2O. So whether it is a reaction of alcohol with carboxylic acid or phenol with carboxylic acid, it forms a ester. Similarly, when you consider the reaction of alcohol with acid anhydride, here also acid anhydride supplies an acyl group, and hence we get the corresponding product as a ester, along with it a byproduct obtained is an acid. Similarly, if you consider the reaction of a phenol also, here also we see that H is removed and substituted by an acyl group. Here we have taken the reactant as acetic anhydride. So one of the acyl group is given in place of H, and the byproduct obtained is CH3C double bond OH. So whether it is alcohol or phenol, it forms ester. Next, we'll consider the reaction of alcohol with acyl chloride in the presence of pyridine. So here also hydrogen is removed and substituted by an acyl group. So the resulting product obtained here is CH3O, then C double bond O, CH3. So here plus of HCl, again we get ester as a product. Similarly with phenol also we get the product as H goes to the place of acyl, acyl to the place of H, and we get the product as benzene ring as it is, oxygen, and to that oxygen acyl group C double bond OCH3, plus of the byproduct obtained is HCl. So pyridine is used to decrease the effect of HCl so that we get more amount of product, and hence the reaction is carried out in the presence of a base. Next very important reaction, again from your theory point of view, that is acetylation of salicylic acid. So when salicylic acid reacts with acid anhydride, it results in the formation, it undergoes esterification reaction, and it results in the formation of acetyl salicylic acid, that is H is removed and substituted by acyl group, plus of byproduct obtained is CH3COOH. So this product what we have got here, we call it as acetyl salicylic acid. Remember its molecular formula, structural formula, as well as its name, that is it is nothing but it is aspirin. So aspirin is acetyl salicylic acid, as well as its structural formula you should know, and it's important for theory exams as well. Next we'll consider the reaction of alkyl halides with Lucas reagent. So what is Lucas reagent? Lucas reagent is anhydrous zinc chloride with concentrated HCl. And what's the work of this Lucas reagent? It is used to distinguish between primary, secondary and tertiary alcohol. How the reaction occurs we'll consider. So if you consider a primary alcohol with HCl, on heating it results in the formation of primary alkyl halide, which gives a white precipitate, or we say that turbidity appears. So turbidity appears due to the formation of alkyl halide, That is, we call it as a primary alkyl halide. So turbidity appears, but appears after heating, and along with it the byproduct obtained here is H2O. So turbidity occurs due to the formation of primary alkyl halide, but after heating. Similarly, we'll go with the second one, that is second type of alcohol, that is secondary alcohol. Secondary alcohol, when it reacts with glucose reagent, you get the product after 5 to 10 minutes. That is, a turbidity appears, a white precipitate appears, and why that white precipitate appears? It's due to the formation of secondary alkyl halide. Since the secondary alkyl halide is formed, it results in the formation of turbidity. Along with it, the byproduct obtained is H2O. And instead of it, if you take a tertiary alcohol with glucose reagent, immediately as soon as you mix HCl in the presence of zinc chloride, you get a turbidity. And why you get a turbidity? It is due to the formation of a tertiary alkyl halide. Along with it, the byproduct obtained is H2O. So since tertiary alkyl halide is formed from tertiary alcohol, we say that immediately tertiary are more easily reacting than secondary than primary. So primary alcohols on heating give turbidity, secondary alcohols after 5 to 10 minutes give turbidity, and tertiary alcohols give turbidity immediately. So we can say that tertiary are more reactive than secondary and secondary than primary. Similarly, we'll consider the next reaction, that is dehydration of alcohol. So when ethanol undergoes dehydration, it results in the formation of ethene plus water. But when you compare it with the secondary alcohol, we see that the percentage of acid decreases, temperature also decreases. It's also a dehydration reaction. It results in the formation of propene, that is removal of OH group from the alpha carbon atom and from beta hydrogen, and the resulting product is propene, but the temperature conditions decreases. Hence we say that secondary are more reactive than primary. And when you consider tertiary, you see here for primary it was H2SO4, secondary 85% H3PO4, and here 20%, and even the temperature is almost least here when compared to the above. So the product obtained is easily a alkene only due to dehydration, that is 2-methyl propene by the loss of water molecule. But since we see the change in the concentration of acid and concentration and the temperature for 3 different alcohol, we can come at the conclusion that tertiary easily undergo dehydration when compared to secondary, and secondary more easily than primary. So we can say that here the correct order of dehydration of alcohol is tertiary are easily undergoing the breaking of COH bond and hence are more reactive than secondary than primary. Next is oxidation reaction. So when you consider oxidation reactions, we see that the primary alcohols are always undergoing oxidation under 2 different conditions. So what are those 2 different conditions we'll consider? One is in the presence of mild oxidizing agent, another is in the presence of strong oxidizing agent. In mild oxidizing agent, it forms aldehyde, and in the presence of strong oxidizing agent, it results in the formation of carboxylic acid. So when it forms carboxylic acid with strong oxidizing agent, now we'll go with mild oxidizing agent. So a primary alcohol with chromic oxide forms aldehyde, or even with PCC it forms aldehyde. Here also if you consider it's a primary alcohol with PCC, it results into a formation of aldehyde. Double bond is unaffected and hence the product obtained is aldehyde, that is primary alcohols are converted to aldehydes by oxidation with mild oxidizing agent. So what is PCC? You may get as a question for 1 mark. It is a mild oxidizing agent. PCC is named as pyridinium chlorochromate. And what is this pyridinium chlorochromate? It is a complex of chromium trioxide with pyridine and HCl. Similarly, we'll consider the reactions of ketones as well. So here when you consider the reaction of ketone with mild oxidizing agent, reaction for formation of ketone with mild oxidizing agent, it's seen that secondary alcohol easily undergoes the reaction and you get the product as a ketone. So here product obtained is a ketone even with mild oxidizing agent. So on oxidation, secondary alcohols form ketone. Next, when vapors of primary alcohol, we can take later example as ethyl alcohol, are passed over heated copper at 573 Kelvin or 300 degrees Celsius, it undergoes dehydrogenation to form aldehyde. In the same way, the secondary alcohol, that is isopropyl alcohol, it results in the formation of ketone by the removal of hydrogen, and hence we say that it forms a ketone. Primary alcohol forms aldehyde, whereas the secondary alcohols always form ketone, remember it. And these both reactions include removal of hydrogen, hence we call them as hydrogenation reaction. So these both we refer them as removal of hydrogen, so dehydrogenation reaction. So dehydrogenation reaction occurs here and resulting product are aldehyde and ketone. But if you take a tertiary alcohol, dehydrogenation does not occur. Instead of it, elimination reaction occur, and the corresponding product obtained is a propene due to the loss of water, and this reaction we call it as dehydration reaction. Primary alcohol from aldehyde, secondary alcohol from ketone, tertiary alcohol from alkene by dehydration reaction. Next, we'll consider the reaction of phenol. So when phenol undergoes certain reactions, I have grouped it under one concept. So we'll try to understand it. With dilute nitric acid, phenol gives you a mixture of two different products as it is an ortho-para directing group. Phenol gives you orthonitrophenol, and along with it another product obtained is para-nitrophenol. So resulting product one is orthonitrophenol, another is para-nitrophenol. So orthonitrophenol is highly volatile, or you can say that it is steam volatile. It easily gets evaporated. And what is the reason why it gets easily evaporated or why it is steam volatile is due to the presence of intramolecular hydrogen bonding. So due to intramolecular hydrogen bonding, phenol results in the formation of orthonitrophenol, which is steam volatile, and para-nitrophenol is less volatile because it forms intermolecular hydrogen bonding, and since it forms intermolecular hydrogen bonding, it is less volatile. So you may get 1 mark questions or multiple choice questions on these concepts as well. So here para-nitrophenol is less volatile, orthonitrophenol is steam volatile. Next, we'll consider the reaction with concentrated nitric acid. With concentrated nitric acid, phenol forms a tri-substituted product, and that tri-substituted product is 2,4,6 trinitrophenol. So 2,4,6 trinitrophenol is obtained as a product, and this 2,4,6 trinitrophenol is given a common name. On this you may get a question, that is picric acid. So picric acid itself is 2,4,6 trinitrophenol. Next, we'll consider the reaction of phenol with bromine in carbon disulfide at 273 Kelvin. Here also it gives you a mixture of two different products. One is orthobromophenol and another is parabromophenol. So here with bromine in carbon disulfide, that is in the presence of a non-polar solvent, you get a mixture of ortho and para product. One is orthobromophenol and another is parabromophenol. So two different products are obtained here. Similarly, if you consider the reaction with bromine water, that is in the presence of polar solvent, phenol reacts with bromine water and it results in the formation of a tri-substituted product, and that tri-substituted product is represented as 2,4,6 tribromophenol, which is obtained as a white precipitate. So 2,4,6 tribromophenol obtained as a white precipitate on reaction of phenol with bromine water is again an important question for 2 marks. Next, if you consider the reaction of phenol with zinc dust, it results in the formation of benzene due to oxidation reaction, and this is also an important reaction. Similarly, if you consider the oxidation of phenol with acidified sodium dichromate, it results in the formation of a diketone, which we call it as benzoquinone. So a diketone is obtained and it is called as, or it is named as, benzoquinone. We call it as an conjugated diketone due to the presence of alternate single and double bond. So it's a conjugated diketone which is named as benzoquinone due to the presence of alternate double and triple bond. And two more reaction with respect to it is called base reaction, which results in the formation of salicylic acid, and Raymer-Tiemann reaction, which results in the formation of salicylaldehyde. We will discuss it. So Kolbe's reaction and Raymer-Tiemann reaction. So we'll consider here Kolbe's reaction. When phenol reacts with sodium hydroxide, it results in the formation of sodium phenoxide, and this sodium phenoxide which is formed here. So phenol with sodium hydroxide forms sodium phenoxide, and sodium phenoxide on reaction with a weak electrophile carbon dioxide undergoes substitution at ortho position followed by acidification results in the formation of salicylic acid, and this reaction we call it as Kolbe's reaction. So salicylic acid is obtained as a product. Next, if you consider the next reaction, that is Raymer-Tiemann reaction. When phenol is made to react with a mixture of chloroform and aqueous NaOH, it results in the formation of an intermediate called as substituted benzyl chloride, which on reaction with sodium hydroxide results in the formation of intermediate and introduction of CHO group at ortho position, and which on acidification results in the formation of salicylaldehyde. So salicylaldehyde is obtained as a product. CHO bonded to benzene ring is benzaldehyde. When CHO is bonded to benzene ring with OH at ortho position, we call it as salicylaldehyde, and this reaction we name it as Raymer-Tiemann reaction. So this is Raymer-Tiemann reaction where we see that CHO is at ortho position, and hence Raymer-Tiemann reaction gives salicylaldehyde. Next, we'll go with chemical reactions of ethers. When ethers react with hydrogen halide, the result in the formation of alcohol. Along with it, the byproduct obtained is an alkyl halide. And this alcohol made to react with another molecule of hydrogen halide, it results in the cleavage of another RO bond, and we get the product as again a alkyl halide along with the alkyl halide RX. Along with it, the byproduct obtained is water. Similarly, if you take aryl halide, reaction with hydrogen halide, the result in the formation of phenol, and the byproduct obtained is an alkyl halide, that is RX. The next order of reactivity of hydrogen halides in case of ethers is hydrogen iodide is more reactive than hydrogen bromide, which is more reactive than hydrogen chloride. Next, we'll consider the last part of reactions here, that is electrophilic substitution reactions of anisole. Anisole is an ortho-para directing group, so you get a mixture of ortho and para. So first we'll see bromination, that is Br2 in ethanoic acid. It's also important for 2 marks. And when we see that anisole reacts with bromine, it results in the formation of orthobromoanisole and para-bromoanisole. And whenever you get a mixture of two different products, that is and whenever you get a mixture of two different products, ortho and para-bromoanisole, one is minor, another is major, and we call it as bromination reaction. Next, we'll go with nitration reaction. In nitration reaction, we see that nitrating mixture H2SO4 and HNO3 is used, and here also you get a mixture of two different products. One is orthonitroanisole and another is para-nitroanisole. And here also, if you consider
Orthonitroanisole, which is again obtained in minor amount, and para-nitroanisole obtained, it will be a major product. So orthonitroanisole is a minor product and para-nitroanisole is a major product. Similarly, we'll go with the next reactions, that is both are nothing but Friedel-Crafts reaction. The first one is Friedel-Crafts alkylation reaction and the another is Friedel-Crafts acylation reaction. So similar to bromination nitration, here we see that alkyl group is substituted on anisole. So the product obtained are again a mixture of ortho and para product. One is ortho methyl anisole or orthomethoxytoluene as given in your NCRT, which is a minor product, and along with it substitution at para position occurs, that is we get the product as paramethoxytoluene, and paramethoxytoluene becomes a major product. So always remember para will be major product and ortho will be minor product. Next is acylation, that is substitution of acyl group at ortho and para position with respect to methoxy. So substitution of an acyl group at ortho position and another product will be substitution of acyl group at para position. When acyl group is substituted on benzene ring, we call it as acetophenone. Hence, the first product what we have got will name it as orthomethoxyacetophenone, and orthomethoxyacetophenone is a minor product, whereas paramethoxyacetophenone is the major product. So we will represent it orthomethoxyacetophenone as a minor product and paramethoxyacetophenone as major. Along with it, two more important things you should know is methanol and ethanol. So methanol is obtained from wood spirit, or it was obtained earlier by destructive distillation of wood, and now chemically we can obtain methanol by the reaction of carbon monoxide with that of hydrogen gas. So nowadays we can obtain it by carbon monoxide reacting with hydrogen gas in the presence of the catalyst. So it is that catalyst will represent here, that is zinc oxide and chromic oxide at a particular temperature and pressure, and what it is that also will consider, that is 200 to 300 atmospheric pressure and 573 to 673 Kelvin temperature. The resulting product you get it as ethanol. The product as methanol. Similarly, ethanol, in that the most important part is denaturation of ethanol, that is ethanol is made unfit for drinking by adding pyridine, which gives a foul smell to it, and along with pyridine copper sulfate is also added, and copper sulfate changes the color. So here pyridine and copper sulfate, which change the smell and color, makes the alcohol unfit for drinking. So these are the concepts which you should know before you solve MCQ questions on alcohol, phenols and ethers. Thank you for watching and all the best for exams.